Hello everyone, I'm Akash. In today's video, we will solve a question from the recent CSIR NET December 2023 exam. Question is that f of x with the polynomial x square plus x plus 1 and g of x with the polynomial x square plus x minus 2. Clearly both belongs to polynomial ring z of x because their coefficients are integers. Then which of the following are true? These are the given options. Option 1 state that for every prime p, f of x modulo p is irreducible polynomial in the polynomial ring Zp of x. Option 2 states that there exists a prime p such that g of x modulo p is irreducible polynomial in polynomial ring Zp of x. Option 3 states that f of x is irreducible polynomial in polynomial ring Q of x. And option 4 states that g of x is irreducible polynomial in polynomial ring Q of x. So let's begin the solution. To solve this question, we will use the result. Let f be a field and f of x belongs to the polynomial ring f of x be a polynomial of degree 2 or 3, then f of x is reducible over f if and only if f of x has 0, that is root in f. That is, f of x is reducible polynomial in f of x if and only if f of x has 0, that is root in f. Okay, this is called the reducibility test for the polynomial of degree 2 or 3. So let's use this to solve this question. F of x, which is equals to x square plus x plus 1. Clearly f of x modulo 3 belongs to z3 of x. Because coefficients are reduced to modulo 3, then the coefficient remains same, because 1 modulo 3 again 1 modulo 3 again 1 modulo 3 again 1. Okay, so f of x belongs to z3 of x, and for 1 belongs to z3, f of 1, which is equals to 1 square plus 1 plus 1, which is equals to 3 modulo 3, which is equals to 0. So this implies 0 belongs to z3 is a root, that is 0 of f of x belongs to z3 of x. So f of x has 0 in z3. F of x has 0 in z3. So this implies f of x is reducible over z3. That is, f of x is reducible polynomial in z3 of x. Okay, but option 1 states that for every prime p, f of x modulo p is irreducible polynomial in zp of x. But here we see that for p equals to 3, f of x is reducible polynomial in z by 3z of x. So option 1 is discarded, because for p equals to 3, it is reducible polynomial in z by 3z of x. Now let's verify option 2. For p equals to 2, okay, g of x, which is equals to x square plus x minus 2, okay, belongs to z2 of x. Okay, g of x modulo 2 belongs to z2 of x. and clearly coefficient reduced to modulo 2. Again, if we reduce the coefficient to the modulo 2, we get x square plus x, because minus 2 mod 2, which is again 0. So clearly g of x belongs to polynomial ring Z2 of x, okay, for p equals to 2, and 1 belongs to Z2 is such that g of 1, which is equals to 1 square plus 1, which is equals to 2 modulo 2, which is equals to 0, belongs to Z2. So this implies 1 belongs to Z2 is a root of g of x belongs to Z2 of x. So again, by this result, g of x has a root in Z2 implies g of x is reducible over Z2. That is, g of x is reducible polynomial in Z2 of x. So this implies g of x is reducible polynomial in Z2 of x, that is in z by 2z of x. Now let's verify for p equals to 3, say. Okay, for p equals to 3, g of x, which is equals to x square plus x minus 2, belongs to z3 of x. And again, when we reduce the coefficient modulo 3, these coefficients become x square plus x plus 1. Okay, and again we can see that when for 1 belongs to z3, g of 1, which is equals to 1 square plus 1 plus 1, which is equals to 3 modulo 3, which is again equals to 0. So g of 1 equals to 0. That implies 1 belongs to z3 is a root of g of x in z3. So g of x has a root in z3. So g of x is reducible polynomial over z3. That is, g of x is a reducible polynomial in z3 of x. That is, g of x is a reducible polynomial in z by 3z of x. Now, for p equals to 5, this coefficient reduces to g of x equals to x square plus x plus minus 2 modulo 5. What will the result? 3. Okay. So again we see that for 1 belongs to z5, g of 1 will be 1 square plus 1 plus 3, which is equals to 5 modulo 5. Okay, and result will be 0 belongs to z5. So we can see that 1 belongs to z5 is the root of g of x belongs to z5 of x. So again, g of x has a 0 in z5, so g of x is reducible over z5. Okay, so that is g of x is a reducible polynomial in z5 of x. That is, g of x is a reducible polynomial in z by 5z of x. So we can see that for every prime p, g of x modulo p is reducible polynomial in z by pz of x. G of x is reducible polynomial, but here what option says? It is irreducible polynomial. So option, there exists a prime p such that g of x modulo p is irreducible polynomial in z by pz of x. But we have seen that for every prime p, 1 belongs to zp is a root of g of x. For every prime p, 1 belongs to zp. For example, in case of z5, 1 belongs to z5 is a root. In case of z3, 1 belongs to 1 belongs to z3 is a root. In case of z2, 1 belongs to z2 is a root. And similarly, for all prime p, 1 belongs to zp is a root of g of x in zp of x. So it is reducible as it has a root in zp. So it is a reducible polynomial in zp. So g of x is a reducible polynomial in zp of x. That is, g of x is a reducible polynomial in z by pz of x. So option B state that it is irreducible polynomial. So option B is wrong. Now we can use the same result to solve to verify third and fourth option. Now third option is f of x is irreducible polynomial in q of x. As f of x is a polynomial of degree 2, so it will be reducible in q of x if and only if it has root in Q. Now, what are the roots of f? By quadratic formula, minus b plus minus under root b square minus 4 times AC upon twice A, that is 1. So we can see that minus 1 plus minus under root minus 4 upon 2. So as there is a minus sign in root sign, so the roots are complex. So we can see that f of x has no root in Q. F of x has no root in Q. So f of x is not reducible. F of x is not reducible because if it has a root, if it has a 0, then it is reducible. If it has a no root, then it is not reducible. That is, it is irreducible polynomial in Q of x. So f of x is irreducible polynomial in Q of x because it has no roots in Q. So option 3 is correct because f of x is irreducible polynomial in Q of x. Or we can simply use the cyclotomic irreducibility of cyclotomic polynomial because it is a third cyclotomic polynomial. Cyclotomic polynomial are the polynomials of the form, okay, for p equals to 3, we can see that f of x is x square plus x plus 1. So it is a third cyclotomic polynomial, and we know that the all cyclotomic polynomial, pth cyclotomic polynomial are irreducible in Q. Irreducible polynomial over Q. That is irreducible polynomial in Q of x. So by this result also we can see that f of x is irreducible polynomial in Q of x. So third option is true. The last option, again we use the same result. Just check whether that g of x has root in Q or not. Let's find the roots of g of x. By the quadratic formula, the roots are minus 1 plus minus under root b square minus 4 times AC upon 2 times A. So the roots are minus 1 plus minus under root 9 by 2. So we can see that there are two roots, they are rational. So g of x has root in Q. So by this result, reducibility test for polynomial of degree 2 or 3, we see that g of x is reducible polynomial over Q. So g of x is reducible polynomial in Q of x. But option said that it is irreducible polynomial. So option is wrong. So the only correct option is f of x is irreducible polynomial in Q of x. So I hope you like the solution and enjoy the video. Thank you for watching. Please like and share this video and subscribe to our YouTube channel. Thank you.